Hello, so in this video we are going to look at example problems of identifying intermolecular forces in molecules. So if I take, for example, H2O and H2S, my first question is going to be what IMFs are in each molecule? And the second question I'm going to ask is which molecule has the strongest IMFs? So take a moment to pause the video and try to answer this. If I draw water, it looks like this. If I draw H2S, it also looks like this. Again, draw lone pairs if you want. I just tend to not draw them, but you most definitely should. In fact, I am going to include them. So we know that all molecules have London dispersion. Actually, I'm going to label this molecule 1 and molecule 2. So to answer this question, molecule 1 and molecule 2, molecule 1 has London dispersion. We also know that it's a polar molecule, so it contains dipole-dipole. I'm just going to write it as D. And it also contains hydrogen bonding, because a hydrogen of one molecule of water will be attracted to the oxygen of another molecule of water. Now with hydrogen sulfide, H2S, it contains London dispersion. All molecules contain that. It contains dipole-dipole because it's polar. And this is not an example of hydrogen bonding, because hydrogen bonding, again, hydrogen bonding only exists if a hydrogen is attached to either an oxygen, nitrogen, or fluorine. And because it does not exist in hydrogen sulfide, it only contains those two intermolecular forces. Now, what we talked about with London dispersion forces is the greater the molar mass, the stronger the London dispersion are. So in H2S, those London dispersions will be stronger in H2S. However, those are not the only intermolecular forces that exist in each molecule. And since London dispersion are essentially the weakest, most of the time we don't really have to look at that when comparing strengths, although we definitely don't eliminate that. Now, water is more polar than hydrogen sulfide because the electronegativity differences between oxygen and hydrogen are a lot stronger. Since the same geometry, we already can control for that. It's simply the electronegativity difference that's a lot stronger, and thus the dipole-dipole must be stronger in water. And most importantly, water is the only one that can hydrogen bond out of those two molecules. Therefore, water will have stronger intermolecular forces. Let's try another problem. Oh, whoops, not mean to show that. Now let's take a look at ICl and Br2. So same questions. So ICl will look like this. Now Br2 will look like this. Now, are these molecules polar or nonpolar? I'll give you a minute just to take a look at the problem and see, determine whether they're polar or nonpolar. So at this point, in most problems we mostly have to rely on the molecular geometry and sometimes on the electronegativity. However, both of these are linear molecules, so we do have to rely on electronegativity here. The electronegativity of chlorine is much greater than iodine, so therefore the difference is enough such that the ICl will be polar. This is a polar molecule. Br2, it doesn't matter what the electronegativity really is bromine because they are the same atom, and so there's no electronegativity difference, therefore this is a nonpolar molecule. So what assumptions then can we make about the intermolecular forces present in each molecule? Well, both of them must have London dispersion. And since all nonpolar molecules only have London dispersion, that will be all of it for bromine. Now, all polar molecules must contain dipole-dipole. Now, ICl does not have any hydrogen, so there's let alone any oxygen, nitrogen, or fluorine, so there's no hydrogen bonding. It is not an ionic compound, so there's not going to be ion-ion or ion dipole. Therefore, ICl will have LDFs in dipole-dipole, while bromine will, Br2 will just have LDFs. Now the next thing is to get the molar masses of, you could get the molar masses of each to compare their LDFs. However, with that being said, even if you got the molar masses of them, you'll find out that they're relatively the same molar mass, so they're both around the 160-ish grams per mole, so their LDFs are going to be relatively the same. Not only does ICl have LDFs, but it also has dipole-dipole. And because there are more intermolecular forces in ICl than bromine, it'll have stronger intermolecular forces. Therefore, ICl has stronger intermolecular forces. Now finally, let's take a look at a harder example. Let's take methanol and water. Take some time to try this example out. Now, hopefully you had some time to look at it. So if I drew the structure of methanol, CH3OH, it would look something like this. And obviously for water, now that we've talked about that quite a bit, it would look something like this. Now let's talk about the different types of intermolecular forces present. In methanol, all molecules have London dispersion. So actually I'll write that for water as well. Now methanol, we have a hydrogen bonded to an oxygen, and that will certainly interact with the other oxygen on another molecule, methanol. So we definitely have hydrogen bonding, and since there's that polar region of it, we have dipole-dipole. That polar region being the OH component. Notice that this OH is not a hydroxide ion. It is not ionic. There is no metal or polyatomic ions. It is a covalent bond, so it is not ionic. Now with water, it has LDFs. It has dipole-dipole because it is polar, and it also has hydrogen bonding. So they both have the same types of intermolecular forces. Now, as far as the strength of them, methanol has stronger London dispersion because the molar mass of methanol is greater. You can use your periodic table and get the molar mass. So carbon is about 12, hydrogen is about 1, and oxygen is about 16. So the molar mass of methanol would be about 32 if I did the math correctly. So 12 plus 16 is 28. 28 plus 4 hydrogens, so this should be 32 grams per mole, while water is 18 grams per mole. So the London dispersions are stronger in methanol than water. However, water is more polar because the dipole in water, the oxygen gets a stronger dipole because the electronegativity difference between oxygen and hydrogen is far greater than that of oxygen and carbon. So dipole is strong, but not as strong in oxygen and carbon. So therefore, the dipole-dipole in water is stronger. And finally, as far as hydrogen bonding, this is a trickier part. Water has two sites of hydrogen bonding. It can use this part or this part to do the hydrogen bonding, while it only has one in this compound. There's not another hydrogen on the oxygen, so there's two hydrogens on water, while there's only one in methanol to do the hydrogen bonding. Therefore, water also has stronger hydrogen bonding, and so if we consider everything, LDFs are the weakest intermolecular force, so those are not really going to be as deterministic for the strength of the intermolecular forces, and the strongest intermolecular forces that are out of all these are stronger in water than in methanol. That is, the dipole-dipole is stronger and the hydrogen bonding is stronger, the strongest of those three. Therefore, water will actually have stronger intermolecular forces than methanol. Thank you for watching, and I hope to see you next time.